A parameter, in its common meaning, is a characteristic, feature, or measurable factor that can help in defining a particular system. A parameter is an important element to consider in evaluation or comprehension of an event, project, or situation. Parameter has more specific interpretations in mathematics, logic, linguistics, environmental science, and other disciplines. Mathematical functions. Mathematical functions have one or more arguments that are designated in the definition by variables. A function definition can also contain parameters, but unlike variables, parameters are not listed among the arguments that the function takes. When parameters are present, the definition actually defines a whole family of functions, one for every valid set of values of the parameters. For instance, one could define a general quadratic function by declaring, here, the variable x designates the function's argument, but a, b, and c are parameters that determine which particular quadratic function is being considered. A parameter could be incorporated into the function name to indicate its dependence on the parameter. For instance, one may define the base b of a logarithm by where b is a parameter that indicates which logarithmic function is being used. It is not an argument of the function, and will, for instance, be a constant when considering the derivative. In some informal situations it is a matter of convention whether some or all of the symbols in a function definition are called parameters. However, changing the status of symbols between parameter and variable changes the function as a mathematical object. For instance, the notation for the falling factorial power defines a polynomial function of n, but is not a polynomial function of k. Indeed, in the latter case, it is only defined for non-negative integer arguments. More formal presentations of such situations typically start out with a function of several variables such as is the most fundamental object being considered, then defining functions with fewer variables from the main one by means of currying. Sometimes it is useful to consider all functions with certain parameters as parametric family, i.e., as an index family of functions. Examples from probability theory are given further below. Examples in a section on frequently misused words in his book The Writer's Art. James J. Kilpatrick quoted a letter from a correspondent, giving examples to illustrate the correct use of the word parameter. W.M. Woods, a mathematician, writes, "A variable is one of the many things a parameter is not. The dependent variable, the speed of the car, depends on the independent variable, the position of the gas pedal." Kilpatrick quoting Woods, "Now, the engineers change the lever arms of the linkage. The speed of the car will still depend on the pedal position, but in a different manner. You have changed a parameter." A parametric equalizer is an audio filter that allows the frequency of maximum cut or boost to be set by one control, and the size of the cut or boost by another. These settings, the frequency level of the peak or trough, are two of the parameters of a frequency response curve, and in a two-control equalizer they completely describe the curve. More elaborate parametric equalizers may allow other parameters to be varied, such as skew. These parameters each describe some aspect of the response curve seen as a whole, over all frequencies. A graphic equalizer provides individual level controls for various frequency bands, each of which acts only on that particular frequency band. If asked to imagine the graph of the relationship y equals x2, one typically visualizes a range of values of x, but only one value of a. Of course, a different value of a can be used, generating a different relation between x and y. Thus a is a parameter. It is less variable than the variable x or y, but it is not an explicit constant like the exponent 2. More precisely, changing the parameter gives a different problem, whereas the variations of the variables x and y are part of the problem itself. In calculating income based on wage and hours worked, it is typically assumed that the number of hours worked is easily changed, but the wage is more static. This makes wage a parameter, hours worked an independent variable, and income a dependent variable. Mathematical models in the context of a mathematical model, such as a probability distribution. The distinction between variables and parameters was described by Bard as follows. We refer to the relations which supposedly describe a certain physical situation as a model. Typically, a model consists of one or more equations. The quantities appearing in the equations we classify into variables and parameters. The distinction between these is not always clear-cut, and it frequently depends on the context in which the variables appear. Usually a model is designed to explain the relationships that exist among quantities which can be measured independently in an experiment. These are the variables of the model. To formulate these relationships, however, one frequently introduces constants, which stand for inherent properties of nature. These are the parameters. Analytic geometry. In analytic geometry, curves are often given as the image of some function. The argument of the function is invariably called the parameter. A circle of radius 1 centered at the origin can be specified in more than one form: implicit form, parametric form, where t is the parameter. Hence these equations, which might be called functions elsewhere, are in analytic geometry characterized as parametric equations. In the independent variables are considered as parameters. Mathematical analysis. In mathematical analysis, integrals dependent on a parameter are often considered. These are of the form in this formula: t is the argument of the function f, and on the right-hand side the parameter on which the integral depends. When evaluating the integral, t is held constant, and so it is considered to be a parameter. If we are interested in the value of f for different values of t, we then consider t to be a variable. The quantity x is a dummy variable or variable of integration. Statistics and econometrics. In statistics and econometrics, the probability framework above still holds, but attention shifts to estimating the parameters of a distribution based on observed data, or testing hypotheses about them. In classical estimation, these parameters are considered fixed but unknown, but in Bayesian estimation they are treated as random variables, and their uncertainty is described as a distribution. In estimation theory of statistics, statistic, or estimator refers to samples, whereas parameter, or estimand, refers to populations, where the samples are taken from. A statistic is a numerical characteristic of a sample that can be used as an estimate of the corresponding parameter, the numerical characteristic of the population from which the sample was drawn. For example, the sample mean, denoted, can be used as an estimate of the mean parameter, denoted mu, of the population from which the sample was drawn. Similarly, the sample variance, denoted S2, can be used to estimate the variance parameter, denoted sigma 2, of the population from which the sample was drawn. Is not an unbiased estimate of the population. Standard deviation. See unbiased estimation of standard deviation. It is possible to make statistical inferences without assuming a particular parametric family of probability distributions. In that case, one speaks of non-parametric statistics as opposed to the parametric statistics just described. For example, a test based on Spearman's rank correlation coefficient would be called non-parametric since the statistic is computed from the rank order of the data disregarding their actual values, whereas those based on the Pearson product moment correlation coefficient are parametric tests since it is computed directly from the data values and thus estimates the parameter known as the population correlation. Probability theory. In probability theory, one may describe the distribution of a random variable as belonging to a family of probability distributions, distinguished from each other by the values of a finite number of parameters. For example, one talks about a Poisson distribution with mean value lambda. The function defining the distribution is. This example nicely illustrates the distinction between constants, parameters, and variables. E is Euler's number, a fundamental mathematical constant. The parameter lambda is the mean number of observations of some phenomenon in question, a property characteristic of the system. K is a variable, in this case the number of occurrences of the phenomenon actually observed from a particular sample. If we want to know the probability of observing K1 occurrences, we plug it into the function to get. Without altering the system, we can take multiple samples, which will have a range of values of K, but the system is always characterized by the same lambda. For instance, suppose we have a radioactive sample that emits, on average, 5 particles every 10 minutes. We take measurements of how many particles the sample emits over 10-minute periods. The measurements exhibit different values of K, and if the sample behaves according to Poisson statistics, then each value of K will come up in a proportion given by the probability mass function above. From measurement to measurement, however, lambda remains constant at 5. If we do not alter the system, then the parameter lambda is unchanged from measurement to measurement. If, on the other hand, we modulate the system by replacing the sample with a more radioactive one, then the parameter lambda would increase. Another common distribution is the normal distribution, which has as parameters the mean mu and the variance sigma squared. In these above examples, the distributions of the random variables are completely specified by the type of distribution, i.e., Poisson or normal, and the parameter values, i.e., mean and variance. In such a case, we have a parameterized distribution. It is possible to use the sequence of moments or cumulants as parameters for a probability distribution. See statistical parameter. Computing. In computing, a parameter is defined as a reference or value that is passed to a function, procedure, subroutine, command, or program. For example, a program may be passed the name of a file on which it should perform some function. Computer programming. In computer programming, two notions of parameter are commonly used, and referred to as parameters and arguments, or more formally as a formal parameter and an actual parameter. In casual usage, these are sometimes not distinguished, and the terms parameter and argument are incorrectly used interchangeably. In the definition of a function, such as f equals x plus 2, x is a formal parameter. When the function is evaluated, as in f, or y equals f plus 5, 3 is the actual parameter, the value that is substituted for the formal parameter used in the function definition. Terminology varies between languages. Some computer languages, such as C, define parameter and argument as given here, while Eiffel, for instance, uses an alternative convention. Engineering. In engineering, the term parameter sometimes loosely refers to an individual measured item. This usage isn't consistent, as sometimes the term channel refers to an individual measured item, with parameter referring to the setup information about that channel. Speaking generally, properties are those physical quantities which directly describe the physical attributes of the system. Parameters are those combinations of the properties which suffice to determine the response of the system. Properties can have all sorts of dimensions, depending upon the system being considered. Parameters are dimensionless, or have the dimension of time or its reciprocal. The term can also be used in engineering contexts, however, as it is typically used in the physical sciences. Environmental science. In environmental science, and particularly in chemistry and microbiology, a parameter is used to describe a discrete chemical or microbiological entity which can be assigned a value which is commonly a concentration. The value may also be a logical entity, a statistical result such as a 95 percentile value, or in some cases a subjective value. Linguistics. Within linguistics, the word parameter is almost exclusively used to denote a binary switch in a universal grammar within a principles and parameters framework. Logic. In logic, the parameters passed to an open predicate are called parameters by some authors. Parameters locally defined within the predicate are called variables. This extra distinction pays off when defining substitution. Others just call parameters passed to an open predicate variables. and when defining substitution have to distinguish between free variables and bound variables. Music. In music theory, a parameter denotes an element which may be manipulated separately from the other elements. The term is used particularly for pitch, loudness, duration, and timbre, though theorists or composers have sometimes considered other musical aspects as parameters. The term is particularly used in serial music, where each parameter may follow some specified series. Paul Lansky and George Pearl criticize the extension of the word parameter to this sense, since it is not closely related to its mathematical sense, but it remains common. The term is also common in music production, as the functions of audio processing units are defined by parameters specific to the type of unit.